All right, so if you take a look, I'm not going to necessarily write this down. We'll just kind of talk through it. But if you notice, just kind of putting everything together, first derivative, second derivative, and that's kind of what today is. What we're going to do today, let me go back to the objective for a second. What we're going to do today, only difference, we're still talking concavity, points of inflection, second derivative, but now again, we're going to do it with rational functions. And like I said, I have one or two examples, and we'll just leave it at that. Make it simple. So we're going to see if we can put this together. So first off, number one, when it says the first derivative is positive, what that really says, what you need to be able to read that as, where is the graph increasing? That's what that says. First derivative being positive means where's the graph increasing? So answer should have been from A to B, it's increasing. There he is. And then here's what we're working on, Jack. And then decreasing all the way from B all the way down here to G, it's decreasing, and then increasing again between G and I. Okay, so two intervals of increasing, A to B and G to I. Okay, we look at critical points. Okay, remember that's where the critical points are where you've got maximums, minimums, that kind of stuff. So if we take a look, a maximum at B, you've got a where are we? We got a minimum here at G. D is kind of like a local maximum, if you will. Okay, it looks like it's kind of a high point, if you will. There's your critical points there. Second derivative. When the second derivative, remember that's concavity. So if we're talking about second derivative being negative, we're just saying where's the graph concave down? That's all we're looking for. And so if you look from like A to B, again, or A to C, that part of the graph is concave down. Then it looks like it switches to concave up between C and D here. And then for a little while, again, looks like it switches back. So here's another interval from D to E is concave down. And then everything back after that then is back to concave up. Okay. Number 4, now we're going back to the function. Where is the function positive? That's all that's saying. Anywhere where it's above the x-axis. That's going back to the actual function values. So in this case, from A all the way over to E, and then from H to I. That's where the function is positive. Part F, where's the first derivatives equal to 0? Maximums and minimums. That's what we're looking for. So in this case, B, D, and G. Those three are your maximums and your minimums. Number 6, zeros of the functions. Okay, x-intercepts, A, E, and H. Number 7, where the second derivative equals 0, remember that's your point of inflection. That's where it's changing concavity. So if you take a look, I would say point C right here is one point where it changes from concave down to concave up. And then actually I would say point D is another point of inflection because it changes back. And then point E is another one where it changes back to concave up. Okay, so you're changing kind of 3 different times. Number 8, we're looking at concave up again, second derivative positive. So now we're just looking concave up from C to D, and from E to I, we've got concave up. Number 9, where is the function less than 0? So now we're just looking at where is it negative, anywhere below the x-axis. So from E to H would be what you'd have there. And then the last one, where the first and the second derivative are both negative. So now what we're looking for is where is the graph decreasing and concave down. Okay, so if you're looking at concave down, we said that's from A to C, well, and it's decreasing from B to C, so there's your first interval that's concave down and decreasing. Then we said the other part that's concave down is from D to E, also is decreasing. So there's your two intervals for that one. Okay, in this case B to C and D to E. Okay. How'd you do? Okay, generally get it, even if you didn't get it 100% right. So this is a little bit hard, and we haven't spent a ton of time on it. I just wanted to kind of see where we're at and kind of put it together. Okay. All right, here's your one example for today. Or if we feel like we need a second one, I have a second one, but if you need it. And so what we're going to do with this example is everything we've been talking about this week. We'll do the first derivative test and the second derivative test. We'll put it all together. That's kind of like what number 6 was on your assignment from yesterday. You had to find everything. Increasing, decreasing, max, min, concavity, point of inflection, all that stuff. And your test next week on the day of the exam, this is what it's going to be, just so you know. Okay? Just a couple of these is all it's going to be. Is here's a problem. Can you find the first derivative? Tell me where the graph is increasing, where is it decreasing, where do you have maximums, minimums? Can you do everything? Can you put it all together on problems? That's what it's going to be next week, just so you know. Okay? It won't be very long. It'll be fairly short. It's more like a kind of a quiz than it is a test. So if we start off, in order to answer the first part, we got to do first derivative. Okay? Now, before we do anything, I'm going to start with critical points here. Okay? Because since it's a rational function, not only do I need to know where the first derivative equals 0, remember, it's also where it's undefined, anywhere you'd have vertical asymptotes, which in this case, at x equals -1, you can't have 0 in the denominator. So I know I have a vertical asymptote at -1, and therefore need to check to see what's going on either side of that value. Okay, so there's one of your critical points right there. Okay, now derivative, f prime of x. Back to a quotient rule again. Okay, so low d high, x plus 1 times the derivative of the numerator, which is 1, minus high d low, x minus 2 times the derivative of the denominator, which is 1, all over the square of what's below, denominator squared, x plus 1 squared. And now again, we've talked, you just clean up the numerator. Distribute, combine like terms, just make sure you clean that up. So if we do that, we're going to get basically x plus 1 here, then you'll add a negative x and then a plus 2. So the x's actually will cancel each other out. You got a plus 1 and a plus 2, you're going to end up with 3 over the quantity x plus 1 squared. Oops. So there's your first derivative, okay? Which means right now, we can kind of work our way through our first derivative at least and figure out increasing, decreasing, max, mins. We can do all that, the first derivative test, okay? So at this point, if we start looking at maximums and minimums, remember, that's where the derivative is equal to 0. And where will this equal 0? Nowhere. Because remember, it's when the numerator equals 0, and the numerator is always going to equal 3. There's no values, there's no x's to solve for. So in this case, there will be no maximums or minimums, okay, on this problem. Otherwise, if it wasn't this exact problem, you would have some sort of function in the numerator. You'd set it equal to 0, solve, find your max and mins, okay? But in this case, there are no maximums and minimums because it won't equal 0. Okay? Which means the only critical point I have is at -1, okay? At that vertical asymptote, which means I need to figure out what's happening on either side of -1. That's where we're going to go through and do our little sign test. So in this case, if we do our number line, I say -1 or 1? -1, right? Yeah. So we have -1, and we have to plug in values into our derivative just to see positive, negative, increasing, decreasing, that kind of stuff. So let's say I take -2, and we don't even necessarily need a number, because if you think about it, if I plug something in, first off, numerator, always positive, it's always 3. And denominator, also always positive because it's squared. So positive means we're going to get, regardless of what you plug in, you're always going to get a positive answer. Okay? So this one is increasing on both sides of the asymptote. So there's our, let's put that in. Interval of increasing is from -infinity to -1, union -1 to infinity. Basically everywhere the entire graph is increasing except at -1 because there's a vertical asymptote. And if we put in here decreasing at all, we can just put none, not applicable. Okay? It is not decreasing anywhere. Okay? There is. So there's the first derivative test. There's all the stuff that we did Monday, Tuesday. Now we got to go to the second, the concavity and all that kind of stuff. And so we're going to take our derivative here, which let me just copy that into the next page and we'll keep going. So here's our first derivative. Now we need to take the derivative of that in order to get the second derivative. Right? So this is f prime. We need to do f double prime, but now in this case, because of what I have, do I have to do a quotient rule? No, we can just rewrite this so I can actually do a chain rule instead. So I'm going to rewrite this one to make it easier as 3 times the quantity x plus 1 to the negative second power. And now you can do a chain rule type problem instead, so you don't have to worry about, not that you can't do a quotient rule, you can, if you'd rather do it. But you can also do it this way. So second derivative, if we start taking the derivative, I'm going to bring that out front, we get negative 6 x plus 1 to the negative third power then. Again, don't forget to drop that more negative by 1, okay? Times the derivative of the inside, which technically is just 1. Okay? Derivative of the outside is a power function. Derivative of the inside is just 1. So ultimately, again, I'm going to rewrite this only because whenever you have negative exponents and we're trying to plug stuff in, it doesn't make nearly as much sense. So I'm going to rewrite this so that there aren't negative exponents, which means our second derivative is really negative 6 over x plus 1 cubed. Okay, that's our second derivative. And then again, same thing. If we kept going, if we set this equal to 0, we'll find our point of inflection, if we have one, which in this case, same reasoning as before. This fraction will never equal 0 because it's always going to equal, we don't have any numerator. The numerator will never equal 0. So in this case, we have point of inflection is none. There is no point of inflection. But again, we still have to test our concavity using that same critical point again. That's still, we got to test with that as well. So we still have to use the negative 1. So if we go back, and again, we do the number line with negative 1, but now using our second derivative. And we can plug in and see what's happening. So let's say I plug in negative 2. We have a negative numerator. If I plug in negative 2, I'll get a negative in parentheses. Raised to the third power means I'll get a negative in the denominator. Negative divided by negative gives you a positive answer, which means to the left of the asymptote, it's concave up. Okay? Left of the asymptote, it's concave up. If you go through and let's say we plug in 0, negative in the numerator, that doesn't change, but now we would have a positive denominator raised to the third power, still positive. So negative divided by positive is a negative. So concave, it does switch concavity on either side. Okay? And ultimately, if you put this all together, so let me write this down. So concave up, you would have from negative infinity to negative 1. And concave down, we would have from negative 1 to infinity. And if we put this all together, not that you're going to have to do this, but I want to make sure that since we started with graphs and stuff, I just want to make sure that you understand it. If you were to actually graph this original function based on what we're seeing right here, what you would actually have in this case, there's a horizontal asymptote at 1. Okay. Again, if you go back to the idea of limits for a second, if we have the limits as x goes to infinity, we ignore those two, that simplifies to 1. Okay, so we have a horizontal asymptote at 1, and here's what the graph would actually look like. Let me sketch it here for you. Horizontal asymptote at 1. We said we have a vertical asymptote at negative 1. Okay, we talked about that. And then the concavity, what that tells me without even having to graph anything, if it's positive to the left and negative to the right, that means the curve must be right here. There's your positive, there's your concave up, and here's your concave down. There's your graph right there, okay? So it matches up with the concavity. That's also why there's no point of inflection. It changes concavity on either side of the asymptote. So it's not a point of inflection, it's going over the asymptote, okay? And then same thing we said before about like increasing, decreasing. We said it is increasing basically everywhere. Well, again, if you look at your graph, increasing as you're working left to right, and then you jump to the other side, and then this is also increasing, getting bigger as you work left to right. Okay, so it matches up with everything that we talked about. Okay. How we doing? Okay? Making sense? Like I said, it's nothing new really. It's just rational functions and putting it all together at this point. Okay? So that's where we're at. The only difference, by the way, and the only other example I have, and we're not going to necessarily do this, but I put together another example just in case you needed it. The only difference on this example is you would actually have a relative maximum, relative minimum, unlike that one where we didn't have one. Okay, this one's got a slant asymptote and therefore has a max and a min, but otherwise same kind of idea. Okay, all right. Your assignment, second derivative, concavity worksheet number 2.